Well, welcome. Welcome to the Dr. Data Science webinar series for 21, the true story of a data science project. And very excited to welcome our special guest for this week, this month rather, Adam Faskovitz. Adam really is the lead on this project, so it's in a sense overdue for him to join us. We had Mike, who's the co-lead, give us a description of the project in our first session in January. We've discussed data cleansing and data exploration in some of our initial sessions, but Adam is now going to get into the meat of the project in this our March session. Reminder, the Dr. Data Science takes place every month on the third Wednesday. So our next session will be on April 21st. And you can also see all of our back episodes on YouTube on the TIBCO Dr. Data Science playlist. So do feel free to check that out. Lots of great stuff there from last year covering a variety of topics. And of course, this year we're focusing on just one project, and we're going to go through the length of that project from beginning to end, although there is no real end to a data science project. And we're in part 3 now, features and transformations. So let me just do a quick recap of what we've covered so far. The project is set in high-tech manufacturing, where companies are producing say memory chips, and those are typically produced on these circular wafers. And at the end of the process, you conduct a series of tests on those wafers, and those are represented often as sort of a visual image, indicating which tests have failed or passed, sort of red, or in this case, orange blobs, indicating that something has gone wrong with that particular chip or die on the wafer. And often what happens is you'll get wafers that look just perfectly fine, and you get some that look pretty messed up. And there are particular patterns that are acceptable, just a few dots here and there, but there are some like these circular patterns or big scratches. Those you really want to track down and figure out what's going on. But the number of different patterns and the different varieties and the causes of those are the result of many, many tests and many operational processes that happen over several weeks. So it's an enormous problem. It's very complex. The data involved is huge, not just the tests themselves, but also all of the sensor and process measurements that you take along the way. So how do you take these different patterns that occur? How do you identify them? How do you put them in separate buckets? How do you categorize them? That's a complicated enough problem by itself. And then how do you find the root cause of those problems in these huge factories and these processes that take many weeks? So that's what we're covering in this particular project. Okay, so let's get into the features and transformations. What we've done, as we saw in the previous episode, is that we've taken the wafer data and we've mapped that out in these visual images, and we can actually see some of these patterns begin to emerge, little blotches and so on. And we tried basic clustering techniques in order to discover the types of patterns. So we just treated these as arrays of values, just essentially an unordered list of these die values, these chip values indicating passing a test or some sort of numerical test. And sure enough, the clusters did actually reveal some patterns. We could see the big red spot, or these sort of checkerboard patterns, or something where it's really all sort of monochromatic color. The problem is we found that those clusters, often different clusters, would actually look pretty similar. We also found that the clusters weren't terribly cohesive, and certain patterns that were really ought to belong to that cluster didn't show up. We also had tremendous problems with the size of the data, with null values, and so on. And so what we're going to be talking about today is the type of transformations we have to do, some pretty clever transformations that Adam's going to tell us about, in order to cluster and analyze the wafer map patterns. Now, before we get into that, I just want to talk more generally about transformations. I won't be the first person to point out that it's sort of the unglamorous part of the data scientist's job to take the data that she or he has been given and transform that into something that's suitable, usually tabular in nature, with all the values filled out, sort of nicely behaved in some way, suitable to be plugged into a predictive model. Some standard transformations that people perform, of course, for numerical data, just standardization, sort of centering around mean of 0, standard deviation of 1, or normalization, just normalizing with the max and min so that everything lies between 0 and 1. Those are very standard things. Often you do that before before training a model. Sometimes that's automatically part of the model package. Imputation, essentially filling in null values. That may be just filling in with a simple average or using a regression. Often sort of grouping by, so if you've got sort of missing values of sales, you might group by a particular location or product and use the mean from the previous weeks. Time series often come into it. Imputation and time series is a whole subject by itself. Straight line interpolation, spline interpolation is something we will cover later in this series, actually. Outlier replacement, I think that's sort of self-explanatory, often binning variables to get numerical into categorical form. Categorical coding, kind of the reverse of that. Things like feature and impacting code. Well, we've actually had a whole Dr. Data Science session just on that subject, so feel free to look that up on YouTube. Those are sort of transformations at the variable level. Of course, there are transformations of the whole data set, so aggregations and pivoting and filtering and so on, removing columns, removing rows. And then dimensionality reduction is often a transformation step that happens before we begin modeling. Very simple things, just like looking at correlations and filtering out those columns that are strongly correlated with each other. More advanced things like PCA, using clustering techniques to do variable reduction. And of course, another aspect of the transformation process is actually transforming existing variables to create new variables. In time series, very common techniques around windowing and sessionization in order to look back over history over some period of time and compute aggregates to create new variables. Power transforms are another very common way to take nonlinear relationships and try to make them linear by applying exponential functions and sines and logs and square roots, box cocks, and so on. And then just one line on this slide, but that could explode into a whole thesis of the different way that data scientists will transform and manipulate data in order to create new meaningful business features. I've indicated a couple of these on the diagrams on the right there. These are from my own data science projects over the last number of years that I've found particularly interesting ones. I was talking about windowing and looking over time series. So that's very common in the retail industry where you're looking at the effects of advertising. It's not true that you see an ad on TV and you race out and buy yourself a new TV. Actually, that did happen to me last week, but generally not true. What you tend to see is ads accumulating their impact over time. And so marketers will refer to something called the ad stock function, which essentially says that the effect of advertising is the advertising this week plus some multiple of the previous week and so on. This sort of cumulative relationship. One of my favorite transformations that I've applied in a project recently, I think this is mentioned on one of our blogs. We did some work with Tipping Point, charity here in San Francisco that tries to alleviate problems of income inequality and poverty. And we were looking at the impact of parking tickets on drivers. And one thing we wanted to take into account is sort of income levels for drivers to see if we could sort of normalize that out and see if there were undue impacts. But of course, we don't have income data. But one thing we could look at was the age of the vehicle as sort of a proxy, but we didn't even have the age of the vehicle. So what we did is we actually looked at the sequence of the license plate. Here in California, they essentially, like an odometer, sort of increase one by one. I've got a picture here of my mother's old car, actually from the 50s or 60s. And in Guernsey, where I'm from, a little island in the Channel, all the license plates only have numbers on them. I think it's one of the few places in the world where this is true. So there are only numbers. So it really is sequential there. So you really can tell the age of the vehicle. It's a crude proxy, but actually it helped us come up with some pretty impactful insights into the effect of parking tickets. And as I mentioned, you can read about that on the TIBCO website. Okay, so those are some examples of transformations that data scientists typically do. I want to hand over to Adam now to actually start talking about the transformations that we applied in this project. And they were critical. These were not just, oh, let's, add a few variables here and there. We really could not get very far in this analysis without doing some pretty fundamental transformations of the data. So Adam, maybe you can unmute yourself and give us a little bit of an introduction into why we even started looking at transformations in the first place.
Yeah, I mean, it started out with this very wide, very large set of data that we originally tried to digest. But sometimes it can be hard when you have such large and especially wide volumes of data where, I mean, it's hard to look through, 1,000 variables and try to understand things well. So that's where we kind of ran into our idea of doing some forms of dimensionality reduction to kind of take away these heavily correlated columns that didn't really give that much information, and try to tackle the data to try to find only, the skeleton of actual valuable data in our data set.
And just as a reminder to our viewers, right, as we've seen on previous sessions, the data basically looks like for every wafer coming through the factory lot, we have a series of numerical variables that indicate a pass test for that chip on the wafer, or some numerical result like, I don't know, sort of electrical tolerance, or I don't know what it might be, but it's either a numerical or sort of categorical variable that indicates, is this die okay?
Yep. And it's a series of all these sequential tests that, did it pass this point? Did it go through this point? And then that actually kind of brought about one of our most critical issues, is dealing with null and missing values. And the thing is, though, this wasn't like a normal situation where null values might have some sort of easy interpretation. Instead, because it was a series of these sequential tests, what it meant when we hit a null value, it was often, it had gone through maybe the first 10 tests and it got actual values, but let's say that it failed the 11th test, that would make all of the tests afterwards have missing values. And you can't easily just impute those with like the 0 or the average or something like that, because it had this different interpretation. So
yeah,
that
I can see on just on that wafer there, right? You've got that gray blob. Those are the missing values there.
Yep, those are.
And as a human, right, I can sort of see, well, probably those are probably going to be blue as well, if you sort of extrapolated from around you. But that's a non-trivial thing to think out how to do that.
Yeah, because let's say that we impute it with something like 0. I believe that the 0 is closer to this very light blue here, as well as if you try to impute it with the mean would also be pretty blue, given the fact that the rest of the wafer is very light blue, meaning that it has very low values. So we kind of had to come up with a sophisticated way of looking at things, which we did through this Bessel functions that I'll talk about in a little bit.
Great.
But the couple of points here are, since we had such wide data, it was important for us to basically just pivot our data in a way that made sense. So there are all these different types of ways that these wafer data sets can look like, because this is a bunch of basically XY values on a grid, and it could be hard to just look at on one big data set. But we can pivot this into, just a wafer, just its list of values, and make it more interpretable when we're trying to do our analysis. Another thing that we ran into, obviously, are null values. And the way that we kind of combat this is through these means of dimensionality reduction through our Bessel functions and SVD, singular value decomposition. So dimensionality reduction was a key way for us to try to reduce and handle the data volumes that can often happen with this wafer data. So we had 1,000 die, which are those singular chips, on the wafer, and those contain the measurement values for the wafer, but these can also contain those measurement values for all these different parameters. I mean, there could be 1,000 of these tests, so it's just the way that this data can explode into so much data it can be a lot. So something we wanted to do is we wanted to make it easier to handle, and this is through dimensionality reduction. So we take our raw wafer data, which contain 1,000 die and 10,000 wafers, and we use these Bessel coefficients and this Bessel transformation to drop it down to only 100 coefficients with these 10,000 wafers. Then further on, we do the singular value decomposition to break that down into only 10 modes, so 10 variables by these 10,000 wafers. So that's reducing this by around 100 times, which can be very important when trying to handle such large amounts of data.
Well,
So
just very quickly, what was that last bit there?
course.
The SOM, what is that?
Oh yeah, so the SOM was actually basically what all this dimensionality reduction was trying to lead to, and that's to get to the point where we can do meaningful clustering on our data. And we couldn't really do this without performing these intermediate steps of the Bessel coefficients and the SVD, because doing just clustering on that raw wafer data, we didn't get great results, because like I said, there are these missing values that can actually stop clustering from even happening. There's also these heavily correlated columns that would lead to things, types of clusters that weren't meaningful. But so these steps are to help make this step more effective.
Got it. Okay. I love this diagram because you've got sort of the dimensionality reduction and the feature transformations that reduce the size of the raw data. Then we use clustering as kind of like another dimensionality reduction technique. And I like the idea, it just sort of hit me, that the model itself is kind of like a singular representation of the entire complexity of the data. So at the end of the day, you've got this model that really does take all that complexity and represent it in this vastly reduced form. This is great. That's really a summary of the project in a way.
Yeah, it is. All in one page. So, so our first step here was this Fourier-Bessel transformation, but it has its roots in Fourier transformation, which is a mathematical method that takes something like a pressure signal. So you can imagine this is a time series and this is pressure over time. Now, this one pressure signal on its own can be represented by a decomposition of a bunch of smaller, or not smaller, but multiple signals. So these can be a bunch of sine and cosine waves, and they may look a lot different than the signal on the top. But when you do a linear transformation and you combine these all together, these can now represent this one signal on the top. So it's an interesting way to decompose your data, but also can be valuable when trying to reduce the complexity and only represent this one top wave by just maybe coefficients that represent these smaller waves, or just
I always think of Fourier series as kind of like breaking down a recipe, like a cake or something, into its constituent ingredients. Those ingredients themselves are complex, but they're kind of uniform, simple ingredients that make up the complex whole. So, okay, so Fourier transforms, got you. How does that relate to these waveform maps?
Yeah, so rather than it being a specific wave for pressure, instead we just have this one wafer, right? So this, you could see all of these little small boxes. These are the actual die, the sensor values on this one wafer. But this can also somewhat be interpreted as its own type of wave, in that it has measurement values and it has its own unique signature, you could say. But instead of breaking it down through just this Fourier transform, we're going to do it through Fourier-Bessel transformation, which takes into account the radial nature of this one wafer. So moving on to this next slide. So this one wafer now could be broken down similarly to the way we just looked at the Fourier transform, but instead of those sines and cosine waves, instead it's going to be typical radial patterns. So on the bottom left, you see this spectrum. And what this is it's a series of these typical radial patterns that you might find on something like a circular wafer map. And now this one wafer is represented by how much it looks like this sub pattern, how much it looks like this sub pattern, and it'll get weights for all of these typical radial patterns, and combining those together will now represent this wafer right here as just a series of these coefficients of how much it looks like each of these. So rather than having to maintain all of those 1,000 die values, you can now just represent it as a series of these weights, which can reduce that dimensionality. So rather than those 1,000 die, you now have 100 of these weights instead.
That's really clever. I have this picture in my head of taking like a sine curve and sort of rotating that around to get one of these little disc shapes. It's kind of like a two-dimensional version of a Fourier series, right?
Yep. So, and this is very valuable because it's going to help us with filling out those null values, and it's going to help us break down our data. So on the left here, what you're looking at is our original raw wafer data. You can see that it has those gray null values in here, and it has all sorts of forms of noise that you might expect in a wafer map. So now the advantage of doing our Fourier-Bessel transformations is it's going to do this dimensionality reduction. It's also going to help us handle these null values. So originally there are these 1,000 die on one of these wafers, but we're going to break that down into now just 100 of these coefficients representing this one wafer right here. And as a form of a sanity check, what we're actually going to do is we're going to show what that wafer looks like when it's reconstructed from those 100 Bessel coefficients. So we're actually going to use those 100 coefficients further on in our analysis. But what we're going to do is we can reconstruct this on the right to kind of use this as a sanity check to prove that it was able to handle these null values and also represent our data well. So transforming it back, you'll see that if we look at this wafer number 5, you'll see that there's a lot of these missing values here. And after reconstructing from the Bessel coefficients alone, just those 100 values, and now mapping it back, you'll see that those are not gray anymore. They're imputed with values, but those values kind of make sense. So like I said before, if you just impute those with something like an average, it might just make it all light blue in this section. But if you notice in the rest of the wafers here, you'll see that around the edges, there are these darker blues, meaning that there are higher measurement values. So to impute with just 0 or just the mean doesn't make sense. But what the Fourier-Bessel transformation is able to do is able to pick up the radial nature of this wafer, understand what other wafers with similar shapes might look like, and impute those with values that make sense. So as you can see, that it's darker blue, and
yeah, it smooths it out like that one on the top right as well. Wafer, what is that? Wafer number 12. That's a really nice example. There's lots of little missing values there, but it's really smoothed it out and makes a lot of sense. Yeah, so I guess now you've got these Bessel coefficients, the coefficients of each of these little Fourier transforms. You never actually use the original data again, right? So you've really performed this dimensionality. This is just a sort of a sanity check, as you say. And yeah,
we never like reconstruct these to actually use them in our analysis. We just need to make sure to prove to ourselves that we didn't lose any information after performing this step of dimensionality reduction. We want to make sure that the Fourier transform still worked and it still actually maintained everything well.
Yeah, and of course you've lost some information, right? I mean, we've reduced dimensionality, that has to happen, but it's amazing how much of the original pattern is there, and in some sense it's captured the essence of that pattern without a lot of the noise. It's really,
yeah, it can kind of reduce the amount of noise because it can just map to the common shapes in your data.
Yeah, great.
Yep. So the Fourier-Bessel transformation was an important step, and it had an additional sense of importance because it allowed us to perform singular value decomposition. Singular value decomposition is a very common method for dimensionality reduction, but the one thing about it is that it's not able to handle null values. So just trying to perform that on its own in the beginning, we're not able to do it. So it was a really valuable step, and now we just have these 100 Bessel coefficients, and now on top of that, we're going to do singular value decomposition to further reduce those. And the way that this varies, it's actually kind of similar in the way you can think about it compared to the Fourier-Bessel transformation. So the way we're going to do it is we're going to represent this one wafer here on the bottom right by similarly a series of coefficients or weights, but this time for common patterns within our specific data. So before, the Fourier-Bessel transformation took all types of radial patterns and represented it by that. But in this case, singular value decomposition finds the modes of variation within our data and finds the most important like wafer maps when reconstructing one wafer here. So you can thought so this first wafer map right here held the most amount of variation for the data set. So you can kind of think about it as the most important test when reconstructing this one wafer right here. So you'll see that it's orange, meaning that it has basically just high measurement values throughout the whole wafer. So the first test when trying to reconstruct is, does it have high values throughout or does it have low values throughout? And then it'll get a weight for that one wafer map right here. And they'll go on to the next test. This will be the second most important variable. And so does it have this type of shape? How much does it have that type of shape? And it'll then get a score. So then we can only just get these 10 scores that represent how much one wafer looks like the typical types of patterns and the most important patterns in our data set. And this now, we've gone from 1,000 of these dye values down to only just 10 of these SVD modes that can reconstruct this wafer map and reconstruct it well.
Wow, that's so cool. And let me just make sure I understand. So the Bessel functions are in some sense, they're not independent of the data. I assume you have to take into account some sort of scaling or whatever. And of course, we've made a selection of the type of Bessel functions to use, but they're fairly generic. They don't take that much notice of the data. They're just these sort of generic sine functions at different frequencies. The SVD really takes into account all the data and tries to capture that variation in these modes, like a SVD, like a PCA, and you've got these different components. And this wafer that we're seeing on the bottom there is sort of made up of different degrees of these SVD components.
Yep, and and why that's important, a big thing is, so something like SVD will do a great job of picking up highly correlated variables in your data and understand when there is that high correlation to maybe just only take that into account for just one of those columns. So yeah, SVD is going to be specific to your data and understanding your data, whereas the Fourier-Bessel transformation was that more generic method.
Great.
So the way that we can actually now get back to even just the original purpose of our problem and what we're trying to do here is we're trying to identify common and important patterns in our wafer data. So we want to understand when certain patterns pop up. So all this can be done to try to help us establish a good clustering method to help identify when certain patterns have come up. So now we've gotten to this point where we do our self-organizing maps, which we'll get further into on the next session. But the way that we can kind of prove to ourselves is another form of sanity check that our clustering perform and develop good clusters of our data. Because when we're doing our clustering, we're only using just those 10 values that we eventually get to after SVD. And so if we do clustering on just those 10 values, we could see from the cluster right here, this is just one cluster from our data. And within that cluster, it's all of those wafers and all these look like one another, meaning that only those 10 values can cluster together all these wafers that look like each other. So it makes sure that, okay, these wafers look like each other without having to consider all of these 1,000 dye values. Instead, I just have those 10 and it makes sure that, okay, these are spatially and mathematically close to each other. It's a good thing, and it didn't lose any of its informational integrity after performing all this dimensionality reduction.
That's so great. This is really nice, Adam. It's a nice sequence of not terribly common techniques, well, certainly the Bessel functions, and it's so intuitively clear what's going on here and the impact of this in terms of being able to create these clusters. And as you say, if you just skip to the next slide, next month's session, we're going to have Nico Rode, who's a regular guest here on Dr. Data Science, and also a member of this project that Adam's been leading. And he's going to talk to us about these clustering techniques that we use. Also, of course, very standard techniques like k-means, of course, but also some of these more advanced methods like self-organizing maps, which use deep learning. Great summary, Adam. Just a couple of questions from folks out there. First one is interesting. Have you thought about applying this to other shapes or images?
Yeah, so I would say that the Fourier-Bessel transformation that we did was pretty unique to our specific use case because of this radial nature of the transformation and of that specific method. But singular value decomposition is going to be a great method if one considering something like image data or just any type of other data set, because it's a common way to do this form of dimensionality reduction. It's very strong in considering highly correlated variables, finding those important patterns within the data. And you'll see a ton of examples when you look online of using SVD and things like PCA, which is highly similar to SVD, when decomposing something like an image into its most important parts.
Got it. Okay. And just very quickly, how much data did you have to process? How scalable is this? Can you give us some sense of the type of volume, data volumes that we see sort of in the lab and sort of in practice?
Yeah, I mean, the data set that we just looked at was 10,000 wafers by around 1,000 die. Now, I can't do the math right in my head right now, but it gets into the millions just in our one data set. But that data set could be a weekly or even daily data set in the set of manufacturing. So now we're able to scale this up because these are highly mathematical methods. So these use things like dot products and don't require any forms of like model training that can take a lot of time, but instead can be pretty immediate. In addition, we can use our own tool, TIBCO Data Science, to be able to scale this out when we hit really, really large volumes of data, which can happen because not only do we have just what I said of the 10,000 wafers and 1,000 die values, but each of those die values can have hundreds of parameters. So that could really get into a lot of data, but we can use our platform to be able to scale that out and these numeric methods that can help speed things up.
Yeah, I'm glad you mentioned that. We've got a session coming up later in the year. I think it's like session 9 or 10, where we talk particularly about the architecture that we use to roll this out once we started to get into those larger volumes of data and actually consider rolling this out into production. There are a variety of different manufacturing sites that are working with TIBCO on this project. It's a great project. You've done a great job innovating and leading it, Adam. And it's a complex project, as we're going to see. We haven't even got to the modeling bit yet. We've only talked about cleansing the data and transforming it to make it manageable. And we've already hit a number of really interesting techniques. So thanks for leading us through that. And as Adam mentioned, next month we'll be covering clustering using all of the great well-behaved data that Adam's created. So join us for that next time. Thanks, everybody.
Thank you.